It's 3 minutes before.
Harris says we can start now.
Okay, let's start. So good afternoon for our Japanese colleague and good morning for European colleagues. Welcome to the session called Audio Signal Processing and Performance Modeling. And it's a pleasure for me to chair this session. So in this session, we will have 5 presentations. And each presentation, as you can see on the screen, will last 18 minutes or around 18 minutes and a few minutes for the questions. So the English transcription is available. All the presentations are recorded and archived on YouTube channel. And that's it, I think. We will have, yes, for the question session, we will have different tools, so raise your hand button on Zoom and also in the chat and in the Slack channel also. So we have different ways to submit your questions. And we will have about 20 minutes after all the presentation to discuss in a different room, I think. In another room. So it's 8, and let's start with the first speaker. So it's Michael Taenzer from Fraunhofer Institute in Germany. And the presentation is about deep learning-based music instrument recognition. So please.
Okay, thank you very much. Okay, let's share. Okay. Can you see? I hope so.
Yes.
All right. So thanks for the introduction. My name is Michael Taenzer. Oh yeah, good morning from Germany first. Yeah, thanks for being here. And together with my colleagues Stylianos, Mimilakis, and Jakob Abeßer, we did this work on exploring learned feature representations in the domain of deep learning-based music instrument recognition. And before I start with the presentation, let me give you a quick overview of what you can expect here. So I'm going to start with an introduction into the topic, which will lead us to a motivation, or that led to a motivation for us to conduct this work, together with a goal for this work. And then I will also show you the experimental setup, of course, which comes along with a few optimization objectives. And I will talk about the data sets we used. And then I will present you some results from which we can draw some conclusions. Okay, so music instrument classification is a subtask from music information retrieval And the aim of this task is basically that you have any song, you can take any song and you want to detect and identify the instruments that are playing at each time frame, for example. So you want to be able to detect and identify the instruments that are playing at each time frame of the song. And this could, for example, look like this, where you have any song, and if your detection worked, then you can have an activity plot just like this. For example, in this example here, you'd have 3 instruments, and one would be the trumpet, the other one would be the violin, and the other one would be the flute. And then you can see here when it's active and when it's not active. Of course, you can also decide whether you want to detect your instruments directly or on another level. Maybe just the instrument family is enough for you. But that's basically what instrument classification is. And it's very useful for large-scale analysis and automatic tagging of data sets or of music in general. This has quite a few applications, for example, in digital libraries or in search machines, where you want to be able to search or find certain pieces depending on the instruments that you're looking for example. And for that, you need to index all of the data. So this kind of tagging is very useful. And also, music instrument classification can be used to inform other tasks in music information retrieval, such as source separation and automatic transcription. The idea behind source separation here is that you could inform the algorithm and tell what it should look for. And then maybe, that's the assumption, maybe the separation is easier when it knows what to look for. The typical challenges in music instrument classification are polyphonic and multi-timbral scenarios, actually, where you have several instruments playing at once and possibly even playing the same note, because then you can have a large overlap in harmonics. So this makes it quite difficult for any detector to identify instruments. There have been many approaches in the past to tackle this kind of problem, but only in recent years, this has gained some traction in the deep learning domain. So there was this work by Han et al., who proved that convolutional neural networks can lead to state-of-the-art results in music, in predominant instrument recognition in this case, but also on polyphonic music. So that was sort of a seminal work. Then in more recent times, there have been attention mechanisms included in CNNs. And basically an attention mechanism is like a weighting function where frame level predictions receive some sort of relevance weighting in relation to a weak label that is given in a data set. Because you can have strongly labeled data sets and weakly labeled data sets, of course. This also led to new state-of-the-art results. And it is assumed that these attention mechanisms are responsible for these results. Then most recently, actually just a month ago at the last Izmir, there was a new work that applied hierarchical structure right into the model. And it's basically, it allows to divide instruments into different levels so that you can have, just as I showed you here on this image, where you have 2 levels, you can actually use that information directly inside a model. And doing this will lead to much less severe errors and in turn to a better generalizability of the predictions. So this is a really promising approach, and again leads to new, very good results. So let's look at the typical pipeline of an instrument recognition system in deep learning. So typically you would have these three building blocks: a pre-processing module, an embedding extraction module, and a classification module. And also typically this would look something like this, where in the pre-processing you would have your frequency representation. You could do your signal representation. You can also do harmonic percussive separation at this step, or any data normalization. This will yield some features right to your embedding extractor, which is typically a CNN or CRNN, just anything along those lines. And that will yield an intermediate feature representation, which conditions the classifier at the end, which can be quite simple at this point. Just a fully connected layer with a softmax activation, for example, depending on what you want to do. And also typically, these two modules are learned jointly in supervised learning scenarios. But also sometimes, or more often, you will notice that pre-processing makes use of pre-trained CNNs actually in order to obtain a feature representation that is relatively powerful in or that has relatively strong discriminative power. And one way to do that is to just employ VGG-ish, for example, or OpenL3 embeddings. But that actually makes use of transfer learning at this point, because you have pre-trained the CNN, and then you input a new signal, which will yield a feature representation. But your two modules here in the end will be learned on a different data set. So actually this makes use of transfer learning. And that is also the core of this work. We want to investigate this kind of pre-trained CNN at this stage. And for that, we use as an example or as a baseline the CNN-based attention mechanism from Gururani et al., which led to very promising results. But it uses a VGG-ish network in the pre-processing stage that was pre-trained on a pretty large data set called the audio set. And we want to discover the influence of this pre-training on the classification results of this work using several pre-training strategies. So we're going to pre-train this VGG-ish network in several different ways, and we're going to look at the results, what's going to happen to the classification results on music instrument classification. So this is going to be our experimental setup. For that, we look at the typical structure again, just to correlate it with what we're going to do. Our pre-processing module is going to look like this. Here we have our log-mal representation, followed by the VGG-ish, and then it kind of branches out. It is followed by a principal component analysis, and then by an 8-bit quantization, which then leads to the final representation. This normalization block you can ignore for the second. I will come back to this later. This final representation is then fed into the embedding extractor. So this is made up of the CNN, of the actual CNN, and the attention mechanism. And then at the end, we just have our classifier. Now, looking at this full pipeline and taking this upper branch without the normalization, this is actually the original baseline from Gururani. All right, so this is what the algorithm looks like. And for the colors, let me quickly explain the colors, but it's basically what I've already said. So green just means that these are modules that have been pre-trained on a different data set, where the yellow modules are actually designated for instrument classification. So these ones are trained on yet again on another data set. Yes, and you can see that we have combined them in a first stage and in the second stage, just for these very reasons. Now, since we want to pre-train the VGG-ish here in many different ways, we actually have to add some objective-specific output layer or function. And it would be too much of information for this presentation, but I'm just going to note that for you, that in order to be able to train the VGG-ish, we have to sometimes add an additional layer of function. So that means that the first stage, pre-training, is technically self-contained, right? Because we just want to achieve, or we want to obtain several VGG-ish models that have been trained on different objectives. And here are the objectives. So one of them is a textual description. What that means is that we are taking inspiration from the field of audio captioning, which basically means that we want to generate a description, a textual description of the incoming signal. For that, we employ the word-to-vec model. And that enables us to train the VGG-ish and optimize the VGG-ish hyperparameters using this kind of target. Then the next objective is signal recovery. So here we use log-mel frequency representations, signal representations, but they are corrupted in two ways. So one way is corrupted with additive noise, and another is with multiplicative noise. And then we feed that into the VGG-ish, we add denoising autoencoders, and then we hope that the VGG-ish learns the latent information from the corrupted version of the signal. The last objective is audio and tag alignment, where we try to maximize the agreement between audio and tag representations. And we obtain the tags using a technique called koala, which employs co-aligned autoencoders and semantically enriches audio representations. So this is a more sophisticated approach out of all the objectives. This is a more sophisticated approach. And the audio encoder is just the VGG-ish itself at this point. So we have 3 objectives plus the baseline objective. And these are the data sets that we're using for this. So for the baseline, we take the VGG-ish as in the original work, train it on audio set the same way. And the objective is just general purpose audio event detection. And as you can see, the audio set is a pretty big data set. It has almost 6,000 hours of audio and over 600 different audio event classes. Then for the textual description and the signal recovery, we use the N-synth. For audio and tag alignment, we use free sound. Then in the second stage, you'll see that we will always use open mic, because this is a data set that contains polyphonic music recordings on 20 instrument classes. So it is that is the data set that we want to evaluate our algorithm on. Yeah, and again, we use the same splits as the original authors. Okay. And these are the results that we're getting for this. So right off the bat, you can see that training this pipeline on the on the general purpose audio event detection leads to the best results, right? And now you can see that we have this twice here. So once we have this post-processed and another time it's normalized. And this really just means the difference between these two branches. So the post-processed version is actually the original baseline version, going the PCA and 8-bit quantization route. And the normalization skips these 2 blocks up here and just does a simple scaling of the feature representation from the VGG-ish into the range of 0 and 1. And you can see that the results are basically the same. Like it looks like there's just a random error in here. And for that reason, we skip the post-processing and just use the normalization and all of the other results. So this simplifies the approach a little bit. Next, what you can see is when you take the VGG-ish and just randomly initialize it, then the performance drops dramatically. And these are, oh yeah, maybe I should mention that these are the macro F1 scores averaged over all the instrument classes in the open mic data set. right? So you can see that the performance on classification immediately drops like significantly when the VGG is just randomly initialized. But then, interestingly, when you look at the log-mel representation, and you just take that directly, basically skipping the VGG at this point, the difference is not very big. And this is quite interesting because log-mel is actually a very common frequency signal representation in music information retrieval. Then for the VGG is trained on NSynth, you can see that they all appear in the same region for all three objectives: textual description, and signal recovery from additive noise and multiplicative noise. They're just slightly better than the log-mel. And then the more sophisticated approach, when using the tag alignment, we get a considerably higher result than all of the other approaches, but it's still significantly below the audio set VGG-ish. And this leads to the conclusion that in the CNN-based attention mechanism, discriminative objectives in conjunction with large data sets are also important factors for achieving good results. And another thing that is noticeable is that using audio tags for computing representation is actually sort of an attractive objective because it can yield competing performance, as you can see here. It's much better than all of the other approaches, unless you have a large data set like audio set, of course. So this opens some future research directions where you can investigate training objectives that take advantage of, for example, general audio and annotations, or the exploitation of multimodalities and everything in a self-supervised manner, for example. And with that, I would just like to show you the references we used. And then I would like to say thank you for your attention.
Thank you. Thank you, Michael. So we have time for questions. So please use the raise the hand in the Zoom or in the chat or by the Slack channel, I think.
I cannot see the chat.
The chat. The discussion. Yes, we have a question from Brendan. Please.
Hi, Michael. Thanks very much for the presentation. Very interesting stuff. I'm also doing work on this type of transfer learning, and I was wondering, with the VGG-ish model, how do you decide how many layers of weights to freeze, and also reciprocally, how many layers are appended for the instrument recognition portion of the model?
That's quite a specific question. Like it really depends. You can still see my slides, right? So it really depends on the objective. Like I said here, so we had to add some layers and functions, but that was also due to the fact that we wanted to make the VGG-ish trainable, you know, because every time you have a different target here. So for the word-to-vec model, for example, you have a vector in the end of, I don't know, like 300 dimensions, I think, because that's what the word-to-vec generates. And you kind of have to adapt that. You kind of have to adapt the VGG-ish to that by, for example, adding fully connected layers, right? With 300 units, for example. But it would be different for the signal recovery, where we use autoencoders. And yeah, so I don't actually know from the top of my head how many layers we employed for each of these. But it really depends. So you're kind of free, honestly. So probably if you have some sophisticated model to train, like some sophisticated approach in order to train your VGGH according to these objectives, then you can probably even change these results here a little bit. So that's what I think I mentioned this, but I think the approach that we took for the NSYNC here with the textual and denoising objectives, they are probably a bit naive, actually. And that may be why the results are not that good for this data set, even though it is relatively big. Yes, so I think that makes sense, because the align objective has a very sophisticated approach. Actually, this is a distinctive work, actually. So it uses co-aligned autoencoders with semantically enriched audio representations, and this is why I don't know how to say this. So, but this may be a reason why the result here is better, because the VGGH has been aligned to it better. You know, I hope this made sense.
Okay, thank you. Yeah, that makes sense. Thanks very much.
Mm-hmm.
Thank you. We have time for one question. No. I was just wondering, I'm not very familiar in the domain, but for the data set you choose for the pre-training, so it's different from the one you choose for the second stage. And how did you choose the data set? Is it random, or the 8 kilo hours of audio, for example? How did you choose that?
There is the dataset split is described in, well, actually, for audio set, we didn't have to do much, because there is a VGGH that is pre-trained on it, so you can literally just take it. Okay. And it is described in this work here from Gururani et al. So that is quite convenient at this point, because we didn't have to retrain it. We could just take the exact same baseline as the original authors, and by that reproduce the results. Okay. We only had to retrain the VGGH on the other data sets, like NSYNC and Freesound.
Okay. And for the choice, it's
yes, for NSYNC, we basically took a random. Mm-hmm. Yeah, I think we took actually two approaches. So one random subset and one smaller subset. But I think we took all data here. Okay. Because, yeah, I think we did, because this is there's so many objectives involved here, and so many different.
Okay. Okay. Thank you. It's time for the next presentation, but we have time to talk later for the other participants. Thank you, Michael.
Yeah, thank you as well.
So the next speaker is André Ofner from Otto van Guericke University. Sorry for my presentation, in Germany. And the presentation is about the predictive coding model for audio analysis and synthesis. So please.
All right. Thanks for the introduction. I hope you can see the slides and hear me. Yes. So my name is André Ofner. This work was done jointly with Johannes Schleiss and Sebastian Stober. I want to talk about hierarchical predictive coding. That's a theory that originated in the cognitive neuroscience area. And I want to talk about how that transfers to audio analysis and synthesis. So just to give a like high-level overview of what predictive coding actually is. So like I mentioned, it originated in cognitive neuroscience and psychology as a theory of brain function. So it tries to describe what neurons and ensembles of neurons have to do in order to lead to the cognition that we see in humans. So the general idea is that brains basically are very complex prediction machines, and that observations are predicted by a generative model of the world that is constantly being refined. And you can actually see your brain doing this by having a look at various optical illusions. I want to focus on the flash lag effect since it also has a temporal component. It's particularly interesting for music and audio applications. So in the flash lag effect, you can see that there's a constant motion going on. So it's a linear circular motion. And then there's a flashing line, which if you would stop the video is actually perfectly aligned to the moving line. But since only the moving part is predicted by your brain, it seems like the flashing line is actually lagging a bit behind. So that's an easy way to get a feel for what predictive coding tries to describe. So we could think about any model trying to implement predictive coding as basically having two parts, where one part is the learned generative model, and the other part is the expected observation. So basically the prediction of the sensory information that the model gets, and information between these two areas is exchanged via predictions. So the learned generative model will try to get very good at predicting what happens. And then information that was surprising is passed towards the model using prediction errors. So these prediction errors can then be weighted basically by the precision of the generative model. Of course, such a model internally will have a certain hierarchy, and probably in the biological brain, this hierarchy is really complex. Here I want to focus on two levels. So if we go back to the flash lag effect, we can see that the model basically describes how high-level information, such as the estimated velocity, will influence more low-level information. So in this case, the estimated velocity would constantly lead to a predicted motion prediction, leading to a detailed description of the estimated appearance at every time step, basically. And finally, there's a prediction about the actual expected observation. So this could be samples of audio or individual pixels in video, just depending on which type of sensory information the model receives. And this means that when we look at the flash lag effect, we have this slight mismatch between the estimated position and the inferred position. So that would be the part that actually synthesizes in the model. And the prediction error or mismatch between these two aspects is then the prediction error, which is used for analysis of the observation and can then be used to refine the model. So while this might be interesting, now the question is, how does that actually map to music processing? So we can think of music as having a hierarchical structure. So on the lowest level, what models operating on audio signals typically want to do is being able to predict raw audio. So in extreme case, sample by sample predictions. In layers further up, models should be able to track local changes such as phase and period between events. And finally, in the highest layers of such a model, ideally there is more cognitively complex phenomena happening, such as, for example, structuring entire songs into their structure, or maybe remembering other songs that were heard previously before and kind of forming prior expectations about future content. So as we can see, such a predictive coding model would describe how information between such levels gets propagated basically by repeating this same structure of predicting and refining the model. And as examples, one example that is used a lot in processing of raw audio is linear predictive coding, or LPC. So LPC is a very efficient model for speech compression and synthesis. However, it requires quite complex algorithms and recursive algorithms for filter coefficient and estimation. So here, the maybe most interesting application of LPC is that we can take any speech signal and compress it into slowly varying filter coefficients. So these would be displayed in the middle. And then once we extracted these low-dimensional coefficients, we can feed the fundamental frequency and white noise through the learned filter and actually recover the reconstructed speech. And depending on filter complexity, the reconstruction quality will differ. The crucial part about linear predictive coding is that it's a quite simple and linear predictive model, but it already allows to do quite complex tasks efficiently in the audio DSP field. So as a first step, when trying to connect such relatively simple predictive coding models to maybe more biologically valid ones and maybe deep neural networks in the end, we first had a look at how existing filters and predictive coding networks look in state space form. And interestingly, if we just look at a single layer network or simple trainable filters like the Kalman filter or IIR filters, the update equations actually look really similar. So typically we have the internal state that gets updated and prediction that gets updated at every time step. And these models differ mostly in the amount and interpretation of the inferred parameters, but it's possible to visualize them in exactly the same form and directly compare these models. And as you can see, the Kalman filter and the LPC filter are basically a special type of filter where you can only infer the state or the transition weights at any for any data set. And differentiable filters or predictive coding networks kind of generalize this idea where everything colored in blue now can be learned. So this means that we can still achieve the same functionality. However, we have much more learnable parameters and increased complexity in the learning process. So now the big question is, after seeing that predictive coding relates to this cognitively and biological valid model of human audio processing, how does that actually connect to the efficient filters that are used in DSP? And that's the main question that we wanted to address in the experimental section and the result section of this study. So generally speaking, the main target is to look at how high efficiency and ease of use connects to this bidirectional and hierarchical processing that we have in predictive coding. So for that, we started out with a relatively simple neural network model based on previous work on so-called gradient-based predictive coding. So the idea is that you have a differential model, much like you have in the domain of deep learning. And each layer shown here on the right already does synthesis and analysis like an LPC filter would do. However, now we have neural networks that learn the state transition and the decoding and the encoding steps. And in summary, this resembles a differentiable nonlinear LPC, even in a single layer. And the model is updated using a stochastic gradient descent on the prediction error. It gets a bit more interesting when we now stack this sort of neural network layers, and stacking is quite straightforward. So we can stack multiple layers by connecting their latent states. And the only thing that is different for hidden states compared to the input layer is that they predict the latent states marked in blue instead of the audio signal. Otherwise, the update equations or the learning process is completely the same. While normally, currently, we probably try to train such a network end-to-end. Here, we try to focus on more biological, plausible learning rules. So we're updating each layer in parallel with so-called Hebbian update rules. So just to give a quick, more detailed look at a single layer, basically this structure is repeated everywhere in the network. And you can see this green pathway, which would be the synthesis part. And in parallel, you have the yellow pathway, which is the analysis part. So it will have a look at the prediction errors that are currently there and try to refine the inferred state based on this analysis. So if we now look at what we can actually do with such a structure, we can see that on the lowest level, so when we apply the network just to sample by sample prediction, we can replicate basic filtering functions such as low pass or high pass transfer functions, which normally already require substantial manual tuning depending on the filter type. If we go on, we can see that on a slightly higher level, we can also use the model in its hierarchical form to predict longer sequences, sample by sample. And here's an example for repeated prediction of the same audio input. So the model essentially sees, let's say 10 or 20 times the exact same audio input and will try to update its top-down prediction of what's happening. So it learns a hierarchical prior structure and it can iteratively refine its prediction for the current observation. And as we can see is if we stop the input layer from tracking the audio signal directly, the model really has to learn meaningful top-down predictions. And this learning process can be quite dynamic and fluctuating because the layers basically update independently of each other. However, we can still see that the hierarchical model manages to memorize the correct onset and phase information for single trials and recover the signal, while single layer models cannot do this for single trial experiments. Finally, we also tested as mid-level complexity beat tracking task. So interestingly, the prediction errors in predictive coding networks can directly be used for tasks such as beat tracking. And there's a high similarity to established methods such as using spectral flux. And now if we look at the SMC data set, we can see that the predictive coding network is vastly outperformed by the baseline methods. However, it should be noted that most baselines actually were tuned on this data set. And if we look at slightly smaller but different data set, we can see that we're actually we actually can get comparable performance with the predictive coding network. And as a quick outlook, so we already had a look at how the prediction errors of the predictive coding model would map to human brain signal. And you can see that actually there is somewhat of a linear dependency, at least in terms of prediction error magnitude to brain signals when captured in EEG. And another really interesting direction we think for this work would be to have a look at more complex and efficient biological, plausible, and especially hierarchical audio synthesis. So really comparing towards state-of-the-art deep learning architectures and trying to find a balance between efficiency, accuracy, and biological plausibility. And with that, thanks a lot for your attention.
Thank you, André. So we have time for questions or comments. Yes, we have a question from Michael. Yes, please.
Hi, well, thanks for the presentation. That was really interesting. I have a quick question. I think it was on slide 15. Mm-hmm. Yes, 15.
Here.
Just something I noticed. So I cannot say I understood everything, I'll be honest, but but on this column where it says hierarchical,
yes,
I would like from what you described, I would expect that that both curves kind of smooth into each other, like it becomes less jagged when you have more updates.
Exactly.
But for some reason on update 20, it looks very jagged.
Yeah.
Like 15 and 25 are okay.
Exactly. So what we can see here is really that internally in the updates between the layers, we have really a dynamic process or fluctuations going on. So each layer needs to decide basically to find a balance between the incoming predictions, so the signal that comes from high levels, and outgoing predictions and the prediction errors there, right? Mm-hmm. And initially each layer will probably just focus on the top, the bottom up information because that is reliable and stable. But with ongoing labels, the top down information gets more interesting. So there needs to be a shift to actually integrating that information. And as you can see, is at update 20, there's this kind of peak point where the prediction gets a bit worse. However, after that, the top-down prediction really is integrated into the prediction on the lower level, and that leads to a significantly more accurate prediction compared to update 15, right? So this is basically the transition phase between relying mostly on lower information versus kind of balancing both inputs.
Okay, awesome. Thank you.
Thanks.
Thank you. There another question or comments?
Mm-hmm.
I checked the Slack channel also, I think. No. Yes, maybe I have one question about the future work. You want to check your model on another, yes, on EG, or and you think that your model is general enough to address a large amount of use cases, or do you think there is a limit of your approach or methodology?
I would say there's always limits. So there's a lot of different ways how you would implement, especially the updates in the model. So here we looked specifically at gradient-based predictive coding. But of course, if you map to brain signals, it makes sense to start at simple predictions. So let's say predicting just differences between beats in a song, let's say. And you can do that using different types of implementations. But so far, it seems like mapping prediction errors to the brain works relatively independent of the exact type of model, which is a really interesting insight. So I would not say that the model is generalizable to everything, but detecting simple things like onset prediction errors already works quite well.
Yes. Maybe we have to adapt the prediction error or the criteria of the optimization, maybe.
Exactly. Yeah. So what I think is a crucial aspect is how to integrate time in the model, because typically you do updates in discrete time steps. And the brain probably does not work like that, and instead kind of integrates over continuous time. So models that address that directly, I think, are even more biological plausible.
Yeah. You have top-down processes, but you have also bottom-up processes.
Exactly.
So, yes, we have to take into account different levels of processing.
Exactly. Yeah.
Okay. Thank you. We have 1 minute for last question or comments. So no. Yes. Yes, Iannis, please. Your microphone is not open. Yeah.
A very general question. Since the last slide right now talks about biologically plausible and hierarchical neural audio synthesis, what is your opinion about the cultural aspect of all this, in the sense of the influence of notation history, music theory history, instrumental history, that has notably plays a well-known central role in forming structures.
For sure.
Do you think that this is compatible with what you're doing, or can a bridge be constructed?
Yeah, so right now, of course, we focus on DSP type of applications. So really working with the audio material, which is, you could argue, is still quite perceptual. But predictive coding really describes how prior expectations at different levels would influence this perception. And there's multiple examples that you could think of how you would test things like that. You could think about, having a multimodal model that would, for example, watch people play their instrument, and then you could have a look at, okay, how do expectations based on physical properties of how music is made would inform prediction errors. And then you could go one level higher even and maybe look at the actual scores. So more a symbolic type. Of course, then you have the question of how do you get symbolic information in there. But just in terms of predictive structure, this would fit really well into the overall network. And then, of course, one thing that is largely missing currently is a more general memory, where, let's say, the model would actively create music and have some sort of social interaction and would remember aspect of that. So this this whole aspect of social and cultural interaction is possible, but of course requires much more complex models.
Thank you very much. Very, very interesting. Thank you.
Thanks.
Thank you. So it's time for to go to the next presentation. Thank you. And the next speaker is Brendan O'Connor from Queen Mary University.
Good morning from London.
Yeah, and the presentation is about zero-shot singing technique conversion.
Great. Let me know if you can't see my slides. My name is Brendan O'Connor, and I'm going to present to you my research on zero-shot singing technique conversion. This was supervised by my Simon Dixon and George Fazekas at the Centre for Digital Music at Queen Mary University of London. It was also sponsored and funded by the EPSRC and AHRC Centre for Doctoral Training in Media Arts Technology. So the task we want to achieve is singing technique conversion. So to kind of unpack what that is, first let's talk about singing technique. What we mean by singing technique in this context is the singer's ability to change timbre by adjusting certain configurations in their vocal production, such as adjusting airflow, adjusting vocal folds or vocal tract shape, or sympathetic vibrations in the body. And also because we're dealing with singing, we need to think about how that differs from speech. So singing has a harmonic and rhythmic structure. It has considerably sustained vowels, and it employs relative pitch as well, or at least relative pitch is extremely important. Whereas in speech, we have continuous movement of spectral envelopes, considerably less sustained vowels, and therefore less consonants, which leads to more aperiodicity. There's more consonants, which leads to more aperiodicity. And there's the notion of intonation as well, which is related to relative pitch, but certainly not so strict. Singing technique conversion, well, let's talk about voice conversion first of all. Voice conversion is the ability to change the perceived identity of a voice by shifting the timbral properties to mimic those of a target speaker. While singing technique conversion attempts to keep the identity of the singer the same, while shifting their timbral properties within a realistic timbral variance for that singer, allowing us to explore the timbral maps for different singing techniques. We do believe that there's a considerable amount of industrial demand, or if there isn't, they should really be expecting it at this point. We have things like Audio-Tune, which are able to fine-tune the pitch contours of singing, and we have this notion of voice likeness, such as Vocaloid, but we don't have anything that automates expression. And I think singing techniques, being able to control these, is certainly a considerable stepping stone towards being able to control expression in singing. We intend to use machine learning based approaches, specifically neural networks, to help us dissect the voice and disentangle its key components from one another. So when we're choosing our neural network framework, we need something that is, first of all, a generative model. It needs to, as I said, be able to disentangle the different attributes of the voice. And most importantly, it needs to be able to achieve a zero-shot conversion. And zero-shot conversion is basically the idea of being able to train a network on some set of data and be able to feed it new source and target information that it hasn't seen in the training sets before, and be able to do these conversions convincingly. An auto-BC is a conditioned autoencoder proposed by Etienne et al. And it has all these properties we need. So I'm going to just go through there quickly enough with you guys. Here we have an autoencoder in the left. We're inputting, in our case, MEL spectrograms, which kind of combines linguistic and speaker information. into itself inherently. It goes through the autoencoder and gets reduced into a bottleneck dimensional size of a smaller dimensional space, and goes through the decoder and is decompressed to create the full MEL spectrogram once again. So one thing we need for this is to be able to feed it some conditioned element, and we condition this autoencoder on voice identity embeddings, which are generated from a pre-trained autoencoder for voice identity. And if we condition the autoencoder on these embeddings, it should prioritize the linguistic content at the bottleneck point, as it's already been given the embedding information constantly. It only needs to concern itself with getting the linguistic content correct. And by restricting the bottleneck size to have minimum capacity to only contain non-timbre information, that would allow us to efficiently disentangle linguistic content from speaker content. Yes, the other thing is during training, the input to the autoencoder is from the same speaker as the input to the voice identity encoder. However, once this is completely trained, we can achieve conversion by swapping out the source and target embeddings for one another. So we'll be swapping out the speakers in X1, so that's not the same as S1, and that allows us to create speaker convergence or speaker conversion. What we want to do is slightly different to that. We want to achieve singing technique conversion. So what we need to do really is take the voice identity decoder and replace that with a singing technique encoder. And the way we've done that is, we train a singing technique encoder. We train it as a classifier on the techniques, the singing techniques for the examples from vocal set. And vocal set is basically a collection of song utterances, usually in the form of scales or arpeggios. And this contains a number of different singing techniques, but the ones we focus on because of their importance to singing are vocal fry, lip trill, breathiness, straight, vibrato, and belt techniques. We used a CRNN architecture, as Michael was talking about earlier on, with an attention layer appended as well for extra insurance. And we found that this gives us 86% accuracy on the test subset we put together from vocal set. This is unlike the architecture that was proposed in the original publication with vocal set, which was just using 3 one-dimensional convolutional layers and 2 dense nets, and that got us 57%. So 86 is a considerable improvement on that, and we found this suitable enough to use as a singing technique encoder. We also trained, we also did clustering analysis on the embedding spaces among the 6 different singing techniques, just to ensure that there was good salience between them, and that embeddings behaved similarly for everything of the same label, of a similar label. Now to talk about the auto STC, which is auto singing technique conversion, I'm going to go through the training and inference behind that. We trained it on 3 different data sets of the voice. That was VCTK, which has examples of speech, MeliDB, which are more realistic examples of solo singing from the stems of a mixed song, and vocal set data set, which, as I mentioned before, are snippets of musical exercises sung by different singers in a way that showcases the different singing techniques of the voice. And we chose these 3 because they which they present the voice very differently and present contrasting material. And we trained the network on different permutations of these, so in different orders. And this was work that was explored by Sahan Nersessian in 2020 on their singing voice conversion tasks. And we found that there is an optimal path that leads towards the minimum loss, which reflects how well our autoencoder is at reconstructing the input spectrogram. And the paths highlighted in bold show us the ideal pathway. So for example, if we're training a network on vocal set data, it's beneficial to first feed it the speech information for 300,000 iterations, then feed it Medley DB data for 150,000 iterations, and then finally vocal set data for a final 50,000 iterations. And you can see a similar path in the grid for that's trained to work with Medley DB. One other thing to note is that we found in the original paper of AutoVC, the authors talk about having a reconstruction loss, which is a combination of this decoder loss and postnet loss, which I won't go into right now. But there is an additional latent loss appended as well. Now, latent loss is the idea of taking this reconstructed input and putting it through the network once more, so that our input spectrogram is now the reconstructed input. And that will give us a new bottleneck embedding in the latent space, which we've notated as C1-1. And to get the latent loss, we simply get the L1 loss between the new latent reconstruction and the original latent representation. We found omitting the latent loss allows the network to converge much quicker and perform much better in terms of being able to create audio that sounds very similar to human observers. So with these generations, when we trained the network on these different data sets, we then had to evaluate how good the network was at doing this kind of thing. So we, with some experiments, to evaluate the audio quality and successful disentanglement of our network, we got volunteers to evaluate different technique converted audio snippets from 3 different models and 6 unaltered snippets as well. In the top section here, you can see the form of the question for evaluating specificity, where singers get a, where listeners get a reference track. This reference track would be the converted audio, and they have to select from 6 options down below which candidate option sounds like it has the most similar singing technique as that of the reference recording. And to evaluate naturalness, we use something very similar to generate mean opinion squared values, simply asking the listener to rate how natural the audio is on a scale of 1 to 5. So these are the results that we got. Here we present 2 graphs that show the mean opinion score and specificity of our generated audio examples. And the combination of these 2 graphs gives us an idea as to how well our models perform under different conditions. Similarity score is an average count of correct predictions weighted by the reciprocal of the number of predictions made for the corresponding task. So that might be a mouthful, but all that you need to know is the bottom graph here represents how convincing the model was at converting to a target singing technique. And so there's a few observations we can make from looking at these graphs and the data. There is no correlation, first of all, between the naturalness or the MOS scores. There's no correlation between that and the similarity data. If we look at the similarity data first, we can see that trill and breathiness. First of all, I should say that these graphs are color coordinated by the different conditions. So we had 3 models. Vocal set VS1 stands for a model that was trained just using vocal set data. VS2 was a model that was trained to optimize vocal set data conversion using all 3 data sets in the paths I showed you earlier. And M1 represents represents using those 3 data sets for training, but testing it on optimizing it for the MedleyDB data. We have the other conditions such as gender, source singing technique, and target singing technique. So when we look at trill and vibrato, trill and breathiness, scoring high specificity whenever the target technique was trill or breathy, you can see that they score quite high, and that means that basically our network was good at converting to breathiness and very good at converting to trilliness. However, you can see that vibrato scored the lowest in similarity. And there's a few reasons why that could be, but one is most likely because the data set, vocal set, there's a lot of leakage of the of frequency modulation in other singing techniques as well. So we think that salience that would normally be reserved for vibrato is kind of leaked across the data set, and therefore is not a very clear feature that the model needs to reproduce. We could also say that if we look at the naturalness, that Trillando has scored the lowest, meaning that it's not very natural sounding, even though it was quite obviously a trill singing technique that was attempted. I won't go into that any further because we're running out of time, but the conclusions are simply that the framework is suitable for singing technique conversion, but only under certain conditions. Good reconstruction did not affect the network's ability to convert the singing techniques, and vocal set is not really suitable for pre-training a singing technique encoder, as it lacks multi-labeling and is not very generalizable to other data sets. So this means we want to use unsupervised frameworks in our next iterations of research with more exposure to multiple data sets. Yeah, thanks very much for listening, and I'm happy to take questions.
Thank you. Is there any questions or comments? No. I can start with a question about your results. Can you explain again why did you get the best scores for trees or breath and low scores for vibrato and other stuff?
Yeah, so you can actually hear this recordings of these conversions in the link to the GitHub page as well in my paper, and you can hear for yourself the salience of trillando. So lip trill or trillando is the technique of doing something like this. And breathiness is a very Marilyn Monroe kind of version of singing. And I think these sound very, very different. I think these in general sound very different to a straight singing technique or a belt singing technique. And that's kind of validated in our previous research, which was on timbral mapping, getting the timbral spaces of the singing voice. And the features for lip trill are very apparent, and they're unlike anything the network would try to reproduce, whether for belt straightness or vibrato, and similarly for breathiness. But I suppose the reason it did so poorly for vibrato is, again, because the key components in vibrato were also evident, were also present in other examples of the data set, such as you can still do a belting voice with vibrato attached to it, and singers seem to have difficulty in singing without while removing vibrato necessarily. I think these are mostly classically trained singers, but don't quote me on that. So there is leakage of these vibrato features in other data sets, and I think that's what made the network give it much less importance. We can see that vibrato is actually rated the highest for naturalness, which is quite surprising given how poorly those conversions were. And this could be down to the fact that the network did very little to change the it had very little to go on to change that vibrato, since the frequency modulation feature has kind of been subsidized in importance wise. And it's also possible that people find voice with vibrato to be more natural anyway, regardless of everything else.
And do you have ideas to how to improve your model, or
because of this exclusive labeling on the data set instead of multi-labeling, it'll be better to harness a lot more than just those labels. So we're looking towards more unsupervised methods, such as using a variational autoencoder and Gaussian mixture models to be able to try and locate those dimensions that control the different variances in the voice.
The mixture model is taken into account several parameters, yes? Or you can add weight on, some coefficients or weight on different parameters?
It's mostly about the variational autoencoder and not being able to disentangle the data into key dimensional size, depending on how small we want that dimensional space to be. And we can experiment with these to see which dimensions affect the different variances in voice recordings.
Thank you.
You're welcome.
Any comments or questions? No? In the Slack, there was a question about can I listen to some samples of the results somewhere?
I think I can click on one single example, which won't be very useful to you. But as I mentioned, if you go onto the GitHub, which is linked in the paper, there's lots and lots of examples. I think maybe 30 examples or something that you can listen to.
I will share with you.
Let me play that one more time. Oh, I can't quite get to it because of the Zoom. But if you go onto that GitHub page, you can see all the examples used in these experiments.
Okay, on the GitHub. Okay. Yes, Michael, you have raised your hand.
Yeah, just a quick question. First of all, thanks. It was also really interesting. Here on this results slide, just to confirm, the difference between the purple bars and the yellow bars is between male and female, or what was that again?
No, so the purple and yellow bars, the purple represents the original singing technique, and and how good the network was at doing conversion, given that source singing technique. And the yellow bars represent how good the network performed whenever it had a particular technique to convert to as the target technique. So for example, in the similarity score, we can see that there's very little, the condition of what the singing technique used to be, what the original singing technique was, has very little effect on the specificity score of the model. The cyan colors, I'm not too sure how they appear on your screens, but yeah, these light blue cyan colors represent male and female conditions.
Okay, thanks.
Welcome.
Thank you, Madeline. It's time for the next presentation. So the next speaker is Etienne Thoret from Prism Laboratory. And the presentation is about audio-tactile perception of roughness.
Hi, everyone. Do you hear me well?
Yes.
Yes. Thank you, Mitsuko, for the introduction. So yes, I'm Etienne Thoret. I'm from the Prism laboratories in Marseille. So good morning from Marseille. I will talk about a work which has been done in collaboration with Madeline Fery and Corentin, who are also students in the Prism laboratory, and with Kronland-Martinet and Sølvi Ystad, that are researchers there. And it's about audio-tactile perception of roughness. So auditory roughness has been studied a lot, and it can be described as the perception of very fast fluctuations in sounds. So there are lots and lots of studies which have been done on this topic. And it has been shown its fundamental properties for perceiving speech and music perception. In music, it's obvious for perception like consonance or dissonance of sounds. And from a more psychoacoustical point of view, it also highlights the existence of auditory critical bands, which are fundamental properties of the peripheral auditory systems. And auditory roughness can be exhibited with a very simple situation. And the most canonical one is if you consider the sum of two monochromatic tones, two pure tones of frequencies F1 and F2. And the sum of these two pure tones can be either considered as a sum, as I said, or as a product. And depending on the difference between the two frequencies, our ears also perceive this as either as a sum of two pure tones or as a sinusoid. And for very specific situation, when the ratios between F2 and F1 is in specific ranges, as we will see later, we perceive these sounds as rough. And I will just play back an example of this. Here you have a typical roughness curve. So it characterizes the sensation of roughness when we increase the difference between F2 and F1. So here in the Abeßer, you have the ratio. So it's F2 over F1 from the unison to the octave. And you will listen to three different examples that characterize well the three different situations that we perceive when we vary this ratio. So I will start with a very small ratio that characterize well when we perceive an amplitude modulation that are also called beats. So here you probably listen to perceive one sinusoid which was modulated in amplitude. If I increase a lot the differences between the two frequencies, you will listen to two different tones. And not exactly in the middle, but an intermediate situation is for specific ratios. You will hear something which is more rough, probably. And here, actually, the ears are not able to separate well between the two sinusoids. So you perceive something which is a bit not really modulating and not really two pitches. And this characterizes the auditory roughness. Oops, sorry, you will listen again. Yes. And sorry. And the question we raised in these studies was, what about other modalities? Oh, sorry, it will do the same. And in particular, what about the tactile modality? Can we exhibit the same sensation of roughness in this modality? So it's already known that the auditory and tactile sensory systems share similarities, in particular because they are processing temporal information. And we may wonder whether we perceive also roughness. And what is interesting is that it's possible to produce similar stimuli as the ones I presented you just before with vibrotactile actuators. So we use this kind of actuators that you can have just taking in between two fingers, and to provide the same kind of sensation as auditory roughness. And the research question that we had is, the first one, is roughness perception also shared between the auditory and tactile modalities? And if yes, does it share the same properties? So we set up experiments to test this kind of hypothesis. So we have we generated stimuli based on this canonical situation where we have two pure tones for 6 different frequencies. Actually, there were 6 conditions in the auditory modality and only 5 in the tactile modality because of the range of perception of the audibility in a tactile modalities was lower than in the auditory one. So we just had one condition more in the auditory condition. And we had 12 different frequency ratios between the two frequencies, and which leads to 6 blocks of 60 pairs for the auditory experiment and 5 blocks of 60 pairs for the tactile experiment. And the experiment consisted in pairwise comparisons. So we asked the subject, they were listened to pairs of sounds, and they had to choose which one from the two was the most granular. And we choose the word granular and not the word rough, because tactile roughness may evoke a different kind of sensation, which are not the sensation that we want to investigate here, which is really related to amplitude modulations. And in the tactile domain, it has been used, the word rough, for characterizing like noisy surfaces, which are slightly different from the sensation that we evoke here. So in this experiment, we recruited 18 subjects. 15 were right-handed and 3 left-handed. So it is important because of the tactile experiment. So we led them using the vibrotactile actuators with their dominant hand. And the experiment was not that long. It lasted around 1 hour to make both the auditory and the tactile experiment. And the analysis, I will now switch to the analysis part of the experiment. So for each subject, we constructed a preference matrix, which characterized the way this subject judged the different comparison between the different stimuli. So for each modalities and for each subject, we had this kind of matrices, and we aggregated them between subjects in order to construct a global preference matrix that characterize for our set of stimuli the judgment of roughness between the different pairs. And what is nice with this kind of experiment is that we can compute something which is related to the perception of roughness thanks to the Bradley-Terry algorithm, and which allows to transform this matrix into a kind of density probability function that characterizes for each sound the probability that it is judged more or less rough from the other ones. And we obtain these results. So here I superimposed all the different situations for the two experiments. And in the dashed line, you have the theoretical roughness model provided by Vasilakis. And what is really interesting is that for each of the different conditions and for the two modalities, we obtain something which is coherent with the literatures, meaning that it makes sense, in particular for the auditory perception, because this kind of experiment had already been done by many different researchers. But what is really interesting is that we observe the same kind of result for the tactile modality. And in particular, we can see that the maximum of roughness is changing depending on the frequency situations. And we also had our single auditory situation that works well. So the results are really interesting because they suggest that we could have a common way of processing and perceiving roughness between touch and audition. And it's particularly interesting because the more global goal of this study is in the future to investigate the multisensory integration of roughness. And in particular, we'd like to test whether we could influence the perception of roughness in audition or in tactile by playing back congruent or incongruent stimuli in the other modality. So I want to thank you for your attention, and I'd be happy to answer any question.
Thank you, Etienne. So we have time for questions.
May I ask a question?
Yes, please.
What is the primary application domain of this research?
I think it's a fundamental research I would answer you psychoacoustics for hearing researchers, but more globally from psychophysics. But the applications of this research could also be used for, I'm sure, in industry to understand how to change the sensation of a surface by adding auditory stimulations. Of course, it's very basic situations, but I think it's important to understand the fundamental, not the fundamental, but the way hearing and tactile modalities integrate information, maybe to design new stimuli and new sensations.
How about architectural acoustics, for example? Would that be a possibility? Architectural acoustics.
You mean like to influence architectural acoustics?
For walls.
Oh, I think one application that we might I'm not working. I'm more interested in by the not neuroscience, but the psychophysics of hearing and multisensory integration. But one application which is by which Corentin Bernard in particular is interested in is to use this kind of results for cars and for sorry, I don't find a graphic tablet to change the sensation when you are using like iPads or this kind of tools.
Thank you. Thank you.
I think there is a question in the chat.
Yes.
Did you find interference or bias because of the multimodal of auditory plus tactile? For example, would cochlear implant users have similar granularity? We haven't tried yet. I mean, from an experimental point of view, to provide auditory and tactile stimulation at the same time. We did pilot experiment on ourselves. We had the impression that yes, it's influencing both, but I have no ideas about cochlear implants. I know I'm not expert in this, but I know that they have a very coarse perception of the spectral shape, but they perceive better maybe amplitude modulation. So maybe it could be interesting to make this kind of experiment, but I really don't know, as I haven't done experiment on cochlear implanted patients, especially in higher frequencies. I'm not sure to understand the question, maybe. I think maybe a way to answer, there is, we stopped, we choose only 5 frequencies for the tactile experiment, because the highest frequency that tactile sensation can perceive is around, I think, 800 hertz, while in audition it's like around 20 kilohertz. So maybe we could try to, you mean like influencing the perception of roughness for higher frequencies with lower tactile stimulation? We haven't tried it yet.
Totally.
We only piloted on ourselves by playing with the different actuators, so I wouldn't answer something strong. But yes, we observe. It seems that there are influences between the modalities, but we haven't evaluated precisely these different influences.
This is your next step to associate auditory and tactile?
Yes, yes, but the experiment is already big, because pairwise comparison experiment is a nice design, but it induces a lot of stimuli, and combining the 2 modalities will like increase a lot the number of trials. So we have to choose the good design, and maybe not using pairwise comparison to evaluate this. So we are still at the design choice of the design for the next experiment.
I have a short question about the model, the roughness model. You showed the Mimilakis model, but there are also other models. Why did you choose this one especially?
Why Mimilakis?
Yes.
I think this is the one which embed the most of the. It has been applied for consonance and dissonance perception, which are way more complex than just a roughness sensation. But I think it's really close from the other one. And but yes, you're right. Maybe we should also try to compare with the other one. But I think in this canonical situation, it doesn't make really. It's not really important, because they all model very well this sensation of beats. Maybe if we are interested in by more complex perception, we will have to test with other roughness model.
Yes, like Lehman model.
Yes.
He give roughness as function of frequency and time also, so you can, yeah.
Yes.
And as I understood, there is no equivalent curve for tactile modality.
We haven't found any studies about that, so I would be interested in if someone have one reference. I think there were a few studies on critical bends on tactile sensation, but it's not with the same design. So we haven't found something like this, which is very simple, but which seems not having been tested yet. So
yeah, it's close to the experiment to find the threshold in tactile modality. We can
yes.
Yeah. Okay. Another questions or comments? Maybe a short comment about your conclusion. You say that it may say that there are common processes between audition and tactile modalities. So you have an idea of how, at which level the common processes are, or
maybe
what is common and what is different?
Yes, the thing, but it's more a hypothesis that we haven't tried because we would need to make like electrophysiological measurements maybe, but I think it's very low level processing. So it's not at the cortical level, of course, but I would say more at the peripheral level either for audition, because we know that it's linked to the cochlear processing, probably for the auditory perception, and for the tactile modality have not really a hypothesis on how it can be made, but maybe at the first step of the nervous processes from the tactile system, with which I'm less confident than audition. So I do not prefer to make a strong hypothesis about that, but globally it suggests that there are common way to process this kind of stimuli.
It is interesting because in this range of frequency, it's close to the border between auditory and vibration sensation. So it's you explore the border between the auditory range and the vibratory range. So
yes,
the frontiers.
One thing which is different, maybe not common, is that here we ask the subject to judge the roughness, but in the examples I played back at the beginning of the talk about the situation where the ratio is large. In audition, we perceive 2 pitch, while in tactile, we do not perceive pitch. So we perceive something different, less rough, but which is not a pitch. And I think it's a main difference between these two modalities, is that there are pitch in audition and not in tactile.
Yes. Okay, thank you, Etienne. I see it's the time for the next presentation. Thank you. And the next and the last presentation is made by a duet. So from Ms. Hirayama and Mr. Zannos. And the presentation is about interactive performances in the multimodal context. So please.
Okay. Thank you very much. Can you see it? Can you see the slide?
Yes.
Yes.
Thank you. Hello, everyone. My name is Haruka Hirayama. I'm a composer and I've been teaching at Hokkaido Information University in Japan. For the introduction, I'd like to hand over to Iannis Zannos.
Hello, everybody. Thank you, Haruka, and thanks to CMMR for letting us present this paper. My name is Iannis Zannos, and I teach at the Department of Audiovisual Arts at the Ionia University, which is in Corfu, Greece. The title of our talk is Towards an Aesthetic of Hybrid Performance Practice, incorporating motion tracking, gesture, and telematic techniques in audiovisual performance. In this talk, we will present the results of a collaboration which we had since 2020, when we first presented works involving dance and music at Tama Music Festival in Tokyo. At that point, Professor Hirayama and I found that we would like to collaborate to compare our different approaches. And this is what you're presenting here. We intensified our collaboration last year when we planned and carried out this summer a residency in Hokkaido, Abeßer, where we performed two pieces, one by Professor Hirayama and one by myself. Our common approach is that we use sensors, and we have dancers send motion data using sensors to produce live sound, and sound is the medium of communication through motion. The difference in our approach is that in my work, I try to investigate the relationship of body movement and performer in a telematic context. That means there are many dancers dancing in different places, and this is what we will be actually comparing in more detail. So next, Professor Hirayama will present her work, and afterwards I will present my work, and then we will conclude with a discussion of the differences and similarities. Okay, over to you.
Okay, now I'd like to talk about the system design and interaction approaches between dancers and sound control in People in the Dunes. As general information, the People in the Dunes project is a collaborated work with Bettina Hoffman. She is a visual artist and choreographer based in Montreal. Through the project, we performed in Tokyo, Montreal, as well as Gatineau in Western Quebec between 2018 and 2020, collaborating with local dancers. Hoffman mainly approached from the viewpoint of visual impact as a choreographer, and Hirayama designed the overall interaction systems and sonic expression. In the first experiment of the People in the Dunes 1, the Kinect of Microsoft is used to control recorded sound materials. Here, the presence or absence of movement in a captured performance area is an important element, and it causes different sound materials. For dancers, a monitor display is prepared in which an image is divided into three. So according to the three positions, the triggering sounds are different. Therefore, dancers can give movements having sensors of controlling sounds. For interaction and sound design, the application of MAX is employed. So now please watch an extract. Okay, now I'd like to go next. So next people in the dunes too is the second work of the project. In this work, we started observing movements or gestures of individual dancers carefully, and then methods to create expressive links between sensors, gestures, and sounds were explored. Here, 2 iPhones for each dancer are employed to use built-in sensors, and the data of sensors were collected by Dixon iOS applications. Dixon can send the data with OSC protocol, that is open sound control, and the Max application receives the data. Particularly, acceleration sensor is used here in different ways. Sometimes it is used for triggering sounds or switching purposes by summing up values of XYZ axis. Also, the data of Y-axis of acceleration is used to control sound modulations and volume changes. So from the viewpoint of movement, up and down movements of arms are upright. So that's a picture. Picture one is a window of Max, and this program allows to receive data from iPhone sensors. The second one is a view of rehearsal with Bettina Hoffman, and she is investigating possible gestures touching iPhone on her arm and listening to sound. So now please watch some extracts from people in the dunes too. In this video, every right arm has synthetic sound, and flicking gestures of right hands or arms can change the pitches of synthetic sounds. On the other hand, every left arm has sampled environmental noise sound, for example, chair rotating. Both arms can change volumes of those sounds, that is, dancers can mix different sound materials by moves. So now please watch. Now I'd like to show the next example. In this video, every right arm can trigger recorded sounds by flicking gestures. In this movement, recorded voice sounds are used, and one has Japanese words, one has French words and one has German words. Then their left hand can switch on or off a freeze sound effect. So by switching on the freeze effect while a voice is sounding, it can retain a brief moment of sound. Also, the y-axis of acceleration sensor on left arm can control volumes of pitch-shifted frozen sound. Please watch.
Je marche à côté d'une joie. Dein Audios. D'une joie qui n'est pas à moi. Wo sich Augen treffen. D'une joie à voir. Von einem Buch gehalten. Je marche à côté de moi en joie.
So finally, I'd like to show one more example. In this video, recorded sounds such as traffic sound and laughing voices are used. One y-axis of acceleration sensor changes the playback speed of sound materials, and the other y-axis of acceleration sensor controls volume of sounds. Okay, please watch. Okay, so these are the outcomes of my mapping approaches. And now, again, I'd like to hand over to Professor Zannos.
Thank you very much. Before continuing, may I ask how much time we've got?
You have, sorry, let's check, 5 minutes, around 5 minutes. Yeah, it will be okay?
Make the question short.
Yeah, okay.
6 minutes. Yeah?
Okay, yes.
I set my timer. Okay, excellent. So I go to start screen. So the concept of my piece called ID Fantasy is to create a distributed performance. This is an ongoing project, research project at our university. And we try to have dancers perform in different venues at the same time. So data from dancers' sensors are transmitted between performance venues using OSC groups, as you see in the middle of this diagram. And at each venue, the sound is synthesized in real time based on the data received from the sensors using Super Collider. So at each venue, the sound represents all the dancers. You can have 2 or 3 or more venues. And the dancers coordinate the movement and expression by listening to each other's sound. For sensors, we use a sense stage system by Marija Balman, which is an Arduino-based lightweight wearable sensor system using an XP-based wireless mesh network, and transmits the data finally to a USB coordinator node, which receives the data via USB to the computer and uses Python to translate it to OSC. Finally, SuperCollider receives the data from OSC and relays it to OSC groups, by which way everybody else in the venues receives it. Finally, an OSC group server on the cloud broadcasts the OSC data to everybody that is registered on the cloud on this group. As sound techniques, we used also samples like Professor Hirayama. These were from recordings made in Ueno, Tokyo. And we used several techniques. The first, most simple technique is just to modulate the amplitude and panning. The second was to use granulation with variable grain size, grain rate, and playback rate. And finally, several FFT-based spectral processing techniques which transform the sound more drastically. The challenge is how the performers can understand which performer is performing the sound and also create a dialogue by timing their movements so that they give each other the turns to respond to each other. This we will see in the next videos. This is the video. Do you see the full screen or is it obstructed? Is the full screen visible?
Yes.
Okay. Because I have this strange Zoom window interfering here, which I can't get rid of. This is from the Lisbon performance, which was performed last Saturday at Música Viva in Lisbon. And we'll see on stage Natalie Mandila, who is dancing locally. And in the back plane, we see projected via Zoom, Mary Randu, who is performing in Corfu. This is an initial stage in the performance where we have just simple playback and the dancers get to know each other through the sound. Okay, the next example is an interplay with more complex sounds using spectral processing, and the interplay is much more dynamic. It took quite a lot of training for the dancers to still keep a sense of timing and dialogue. There we go. Okay, finally, my last example is how we developed the algorithms. This is rehearsal where we are going to try to develop the next type of algorithm, which enables the sound to pass only when the dancer is moving, and it's in 3 stages where we are tweaking the sensitivity. Okay.
Νομίζω είναι καλά, ναι, και εγώ. Είναι τόσο όσο κάπως.
Ωραία. Αλλάζω χωρίς να αλλάξω τον αλγόριθμο, αλλάζω την παράμετρο, άλλο λίγο, τώρα το κάνει λιγότερο ευαίσθητο. Θέλει πιο δυνατή κίνηση για να παίξει. Δηλαδή τώρα είναι 5 χιλιοστά.
Ωραία, καλύτερα.
Δεν είναι ότι χιλιοστού που αλλάζω.
Είναι η διαφορά.
Είναι πάρα πολύ μικρό. Το κατεβάζω λιγάκι, ανεβάζω την ευαισθησία λιγάκι τώρα. Και κατεβάζω την ευαισθησία τώρα. Πιο εύκολα σιωπή, εντάξει. Εντάξει.
Ναι. Οπότε το αφήνετε εκεί.
Κατεβάζω, την ανεβάζω στο full, σχεδόν full τώρα. Okay, so this is the way we work. These are the samples, the coding session samples. So besides our videos and the sound, we keep the code, and this is becoming a library of sounds and of settings that is growing. It's instead of training a machine, we train human beings in a way. And brief comparison before we go to the conclusion. So Hirayama is using iPhone, I'm using SenseStage system. As synthesis software, Hirayama is using MaxMSP and I'm using Super Collider. And the synthesis techniques, we have some more convergence here. We both used playback with rate modulation and filters and granulation, synthetic sounds, whereas I use FFT-based spectral manipulation. The big difference is that one performance is local and the other one is distributed. And in our conclusion, we would like to continue exchanging the codes and techniques. I already learned some stuff from our collaboration this summer. And we already converged also in terms of use of hardware. We're looking forward to more convergence and more enriching by collaborating with Japanese and Greek or European dancers in the future. Thank you very much for your attention.
Thank you. So officially it's the end of the session, but we have maybe time for one question before switching to the post-discussion session. Question or comments? Yes, Sølvi?
Hello, everybody. Thank you for this nice presentation. I wonder if you could say some more about the way you mapped, the sound was mapped to the dancer's movement. Did the dancers interfere, or were you the only one who decided how this mapping should be done?
It was during the course of many rehearsals. We did rehearsals that found things that didn't work, and then we changed. So it was trial and error, always with a dancer. So that's how we finally got the kind of control with which the dancer is more comfortable. And you saw one of those rehearsals, the most recent one. And this is what we have in front of us for next year. This is how we work. Okay.
Okay, nice. And do you have some specific do you think that from this work you could kind of establish some kind of rules for mapping sounds to movements?
We will start with a library. I don't know whether I like the word of rules or techniques, but more a library and maybe a language. And actually, this is part of our project. The project that runs here at the Department of Audiovisual Arts has a duration for 1 more year. And we are contracting these dancers who are close friends that work here in Corfu so that we can meet many, many times and videoscope, write, combine with audio recordings and with code. And on the base of that, hopefully we'll have some publications which will give you more details about our language.
Okay, thank you very much.
Thank you. So it's time to close the session. So thank you for all the speakers and for the nice presentations. And we now switch to the breakout rooms. So I'll let the organizers say something or no, we directly switch to the rooms.
Shall we stay on? Excuse me, are we supposed to stay on or do we have to log out and log back in? Are we supposed to?
Yeah. I'll let the organizer answer.
Okay.
Please, Mr. Organizer.
Can you hear me?
Yeah.
Okay. So, so can you move on to the breakout rooms, presenters?
Do we have to log out from this one?
No. So you may find the breakout room button on the bottom of the Zoom
yes,
window. I guess.
Sorry. Which one do we go to? Backup 1, backup 2?
And because your paper is
yes, it's 6.5.
6.5?
Yeah.
Your paper is 6.5?
Yeah, it's the last one.
Then,
yeah.
So please go to the 6.5 room. Okay?
Great. Thank you.
Okay, thanks.